we're gonna look at well, let's see here. Let me make sure that I'm going to be correct about saying this. We're going to look at our, this is really it. We're going to look at our final 2 derivative skills of the whole year. So once we're done with this, there won't be any more like, here's a brand new skill as far as derivatives go. And after like Monday of next week, there won't be any more brand new antiderivative skills either. So we're going to be kind of closing up the skills portion of our year in the next couple of classes, and we'll be moving on to just some applications of all the stuff that we've been working on. Okay, that makes sense? So as you guys know, I feel pretty strongly that math really ought to make sense. Math should be able to be connected to other pieces. So if we do something today and you're like, I don't really understand how this connects to this or that, or why does this work, that kind of thing, feel free to ask. The past couple classes, the last class was kind of a really weird class because we just had to figure out how these rules worked and use them. And I'm not really a fan of that, but knowing our compressed time, kind of had to do something like that. Anyways, so this is it. We're going to be looking at these derivatives of arcsine, arctangent, and then probably the least important of the 3 would be arc cosine, and you'll see that here in a minute. And we'll talk a little bit about why we would even consider these, why these would even be included in our framework for our class, show you how these work, and we'll just do a little practicing with them. Does that make sense? All right. And I'm going to have you guys try to develop a lot of these on your own, or as much as we can, I guess. So let me get the right size screen here, maybe something like that. So I want to focus on that first sentence right there. We're only going to be focusing on 2 of these inverse trig functions, and that's just a scope thing. And when we could find the derivative of cosecant, cotangent, that kind of stuff too. But we're not, just from a scope perspective, we really don't need to. We can get to everything we need to with just 2 of these. And then down below, I put, it might be easier to learn how to derive these instead of memorizing them. Let me just say, it's going to be better for you to understand where they come from. Now, what you do with them, as far as maybe you do end up kind of memorizing because you use them a bunch, I think we'd all be doing ourselves a disservice if we didn't look at where these come from and how they work versus, hey guys, here's some rules, memorize them, if that makes sense. So we'd try to avoid that as much as we can. So what I want to do is, how about this? Why don't I show you the rule? You're not going to have any idea where they come from, and then let me show you where at least 1 or 2 of them come from. Does that work? Okay. So you can copy these down if you want, or you can always just wait until later to copy them down, because we'll go through and kind of prove these as well. So one thing that's really important for us to understand as far as a convention goes, U, like the letter U, is some function in terms of x. So we often use that letter U to represent this. And that's what the U stands for. And A is some constant. So we're being consistent with kind of the typical symbology of a math class. Letters at the end of the alphabet are most often variables. Letters at the start of the alphabet are usually constant. So that's kind of our rules of the game, if that makes sense. All right. So then here are your derivatives. The derivative with respect to x of arcsine of u over a is this. It's u prime over the square root of a squared minus u squared. And like I said, you look at that and you think, where on earth did that come from? Some magical rule, the textbook, whatever. We'll look at it. There's a good reason for this. The next one. Does anybody have just like a totally wild guess as to what the next one might be? Oh, like the reciprocal of it. Yeah. Gotcha. It's not the reciprocal.
Is it a prime?
It's not a prime. A prime would just be 0, right? Because a is a constant.
Okay. So it's u prime over the square root of u prime minus a prime.
Oh, interesting idea.
A squared, sorry.
Not quite. Right, you flip the radicand around, right? Right. Not quite it, but you're kind of hinting around at the right idea. He messed around with the positive, negative inside the radical, right? Any other wild guesses?
It's a negative.
It's a negative what?
Is it just a negative?
What do you mean? It's like
Just a different?
negative of what?
Like negative u prime.
So the negative of the derivative of arcsine? Yes, that's it. Great guess. Well done, Robbie. You get the guessing award for the day. Well done. It's not just like a totally wild guess. I mean, it's not that much different from what Sam was thinking, but you all know that the derivative of sine is cosine, the derivative of cosine is negative sine, so it would be, sort of a logical guess to throw something out there like that, and that's right. I don't think we'll prove that one. The last one we will prove, though. This is arctangent. The derivative of arctangent is a little bit different. It's u prime times a over a squared plus u squared with no square roots. Okay. So let's prove these. And I think you guys all have these written down. I'm going to erase them so that I give myself a little bit more room. Good? Okay, so check this out. I'm going to have you guys do as much of this as we can. Okay, here we go. You ready? Let's start off with this one here. Let's start off with arcsine was the first one. So if I've got arcsine of u over a. So let me ask you this before we kind of go into all these steps here. Look back at the derivative of arcsine of u over a. It's like u prime over square root of a squared minus u squared. Like when you look at the little parts of that, like does anything jump out to you as like, ooh, that could have come from this, or that looks like such and such, whatever?
Like Pythagorean theorem.
Pythagorean theorem. Why Pythagorean theorem?
Well, the square root of something squared and something else squared, like added or subtracted together.
Yeah. And the square rooted
Like a
potentially,
common
obviously.
step, yeah, like square root of something squared.
Does that make sense to you guys? Let's see if that shows up in this derivation. So here we go. Here's how we're going to do this. I'm going to set this up as an equation to make this a little easier to handle. I'm going to write y equals arcsine of u over a. And if y equals arcsine of u over a, wouldn't my goal be to find what?
Y prime.
Y prime or dy dx? Sure. So my goal, I'm going to put dy dx here. You could also put y prime. So if we're going to set this up as we have, which I think is going to be useful, the goal is to find y prime or dy dx. Okay, so there's the relationship there. Y equals arcsine of u over a. Can we just differentiate right away? Can I just go ddx of everything? Well, there's a problem with that, though, right? So if I just do this, if I say, well, let's do ddx of everything, here's the problem. Keep in mind what we're trying to do here. We're trying to prove something. So if I do ddx of everything, ddx of y would be dy dx. And what's ddx of arcsine of u over a? Isn't that the thing we're trying to prove? So like pretending like we really don't know what the answer is, we'd be thinking, I have no idea. Right? So we need to kind of mess around with this this equation before I do any ddxing of anything. What can I do?
I wrote down.
Scratch it out. It's okay. That could be a little note to self. Not the right thing to do. Well, we really can't. I mean, it's not that it's a terrible thing. It's just at this stage of the game, we are acting like we don't have a clue what the derivative of arcsine of u over a is. And so we really can't do that, right? So how could I rewrite this in a different form that's equivalent, has the same relationship, but just a different form?
Is it 1 over sine?
Arcsine is not 1 over sine. That's cosecant.
What's arcsine again?
What do you think, Robbie? Say one more time.
Yeah.
Arcsine is the sign with the little negative one. It's inverse sine, yes. Exactly. You know what? I apologize. I assumed that we had that connection. Let's make sure we understand that. That's a good question. You guys okay with the fact that arcsine is that? Okay, cool. I just want to make sure we're good. You gotta make that connection for sure. So is there, based on that, I mean, it's actually a pretty good thing to point out. Is there any way I could rewrite that to where it has the same relationship, but just is different and maybe in such a way that I could actually handle it? Hey, there we go. Dax said it. Sine of y equals u over a. That make sense? I just did the sine of both sides. So I did, like to go from step 1 to step 2, I did the sine of the left side, and I did the sine of the right side. How does the sine interact with the arc sine? Cancel out completely, right? So that's why the right side, there's no sines or anything over there. It's just u over a. And on the left side, I've got sine of y. Is that good? Okay. So we just rewrote this. Let's think now, could I do d dx? Could I do a derivative of this now? Do I know the derivative of sine?
Mm-hmm.
I do. So let's do it. So if I go back and say, let's do d dx of everything. Remember, we're doing d dx, not ddu, not dda, not ddy, not dd, whatever. It's specifically d dx because we want to find dy dx. What's d dx of sine of y? Cosine of y times y prime or dy dx. That's right. So there's a chain rule involved there. This is actually implicit differentiation, if you guys remember that from the first semester. Okay, now let's remember, this is why I defined this earlier. U is some function in terms of x. A is some constant. So what's the derivative of u over a?
1 over a u prime.
Sure. You could be fooled into doing a quotient rule, which I would not recommend, but it would work. So you could rewrite this as 1 over a times, I'll just put it as u prime. I think that works for us. Still making sense?
Yeah.
All right. So then, remember the goal, I wrote it up here. The goal was to find dy dx. Do you see it? What do I need? Yeah, right, divide. So this would be something like dy dx equals 1 over a cosine y
And then use on the top.
times u prime. That make sense? Why do we have u? I'm not sure what you mean. Like the u prime? Are you sure? Hey, remember what I said at the start? I think you've heard me say this a lot. Math should make sense. So don't tell yourself, oh, it's just some rule I just need to memorize. If something seems off, that should probably be the thing that we focus on. I'll let you keep thinking there. Meg, what do you got?
So if you divide both sides by cosine of y,
Yep.
why aren't you dividing 1 over a multiplied by cosine of y?
Yeah. So here, let me rewrite a little bit for you. So would you be okay if I rewrote this step like this, where it's... does that make sense? Okay. So then if I divide both sides by cosine y, if you go back to like that old stuff, if you've got a fraction divided by something, or something divided by a fraction, or a fraction divided by a fraction, what's that rule? Yeah, so what I would do here is say, these cancel, of course. Dy dx equals, so it'd be u prime over a. There's my copy. Dot. Here is my flop. And then when you multiply fractions together, you just multiply the numerators times each other and the denominators times each other.
Yeah, my brain, I don't know.
That's okay.
You
I
could
skipped a step in there.
You could just multiply both sides times 1 over cosine y.
Yep, same thing.
That way.
Absolutely. Yeah. Jake, your face is saying that you figured something out, maybe? No? I'm misreading you?
U over a becomes 1 over a.
Because A is a constant.
So A is a constant. Yep. U is some function in terms of x. You could be anything. It could be x squared minus x plus 10. It could just be an x. It could be whatever. So we're basically using the constant multiple rule. So I'm pulling the 1 over a out of consideration, doing the derivative to whatever u is, and then multiplying the 1 over a back in. Make sense? Yeah. So then what I want you guys to do now is compare what you have on your paper from earlier for the derivative of arcsine with this. Is that the same? Not really. I mean, the u prime is where it's supposed to be, right? But if I remember right, that rule we looked at earlier, there was like a square root and an a squared minus u squared, and that a hanging out in the denominator wasn't there, and right? So does anybody have any suggestions as to what we can do? Because we're clearly not done, because we'll know that we're done when we have exactly the thing we're supposed to have, right? It's one of those proofs, so it's kind of nice because you know when you're done. Any suggestions on what I could do?
Is it kind of like a distance formula?
Kind of like a distance formula. It kind of is like a distance formula. You could say that. Yep, you could say that. And what is the distance formula foundation? Like what?
Like 2 points.
2 points, and what do we use to kind of develop the distance formula? Like a different concept, but it's like kind of the underlying foundation for the... It's the Pythagorean theorem, which kind of goes with what Sam said at the start. It sort of looked like there's a Pythagorean theorem thing going on, right? Make sense? So here's what I'm going to do. I'm going to try to figure out what cosine of y actually is in terms of some other variables that I need. So here's what I'm going to do. Whenever you've got cosine of whatever, can't you translate that into a triangle?
Mm-hmm.
So I'm going to build a little triangle. I'm going to come up here and say, here is my lovely triangle. And it's going to be a right triangle. And I need to get some labels in there. I'm going to call this angle down here y. We okay with that?
Mm-hmm.
Cosine of y, sine of y. Y is clearly an angle. Okay.
Opposite.
What I'm going to use here, so like to do cosine of y, I need to do adjacent over hypotenuse. And as currently drawn, I don't have a clue what any of the sides are, right? So is there anything up here that might give me an idea of here's what the sides ought to be? What do you see, Sam?
Your original equation, especially easier after you changed it the first time, that one.
Maybe like right there?
Yeah.
Yeah. This tells me that for the angle y, the opposite side is u, and the hypotenuse is a. Right? That's what that's telling me. So I can come back over here and say, all right, for that angle y, the opposite is u, hypotenuse is a. This is neat and everything, except when I do cosine of y, which is what I'm trying to do, I need an adjacent side, which I don't have.
So to find the angle, you have to do the square root of a squared minus u squared.
Yay. So if I do the Pythagorean theorem, so this is my missing angle. We'll call it like b or something if you want. But I'll get rid of that here in a second. Couldn't we say b squared plus u squared equals a squared? Therefore, b is equal to the positive square root of a squared minus u squared. So in place of that kind of useless b, I'm going to put what it equals. So it'd be square root of a squared minus u squared. Following okay? So now we can actually do the cosine of y. So here we go. I end up with dy dx equals u prime over a times, now I'm going to do adjacent over hypotenuse. And you can see it all coming together, and now the last piece of the puzzle fits in. The a's cancel out, don't they? That was the last thing that needed to work. So
How are you dividing by n?
So it's adjacent over hypotenuse for my cosine ratio. And so I did adjacent over hypotenuse.
Okay.
And then you can see at this point we do have the exact formula that we thought we were going to get. It's exactly what we thought it would be. So we know we're done. Question, Kayvon.
So, do we have to, will we ever have to, use that on a test, or can we always use a shortcut?
So it's like, it's kind of the wrong question,
Yes.
right? So,
It's valid.
so listen, it's hard. It's really difficult, especially here at Valor, because we meet such a small amount of time, which I've talked to you guys, and I think you understand that. Like real math, if we really had the time to really do this, I would probably never, ever, ever just tell you what the rule or the procedure is. I present you with a situation and say, well, here's why we maybe would want to do this. Here's your starting point. What do you think? Anybody have any idea on what we ought to do? And we'd spend like 2, 3, 4 days trying to figure out how in the world we do the derivative of a product. But I can tell you for sure, when we get to the end of that 2, 3, 4 days, you probably aren't going to be forgetting that very easily, right? And so, and no school really has that much time to do that kind of thing, because we have finite time, there has to be some kind of give and take with, I got to give you some rules and you have to kind of apply them. And other times, I think this is complicated enough. So, Kayvon, really the long answer to your question is, these are complicated enough. I really don't want to do you the disservice of just saying, hey guys, here's a rule. I'm not going to tell you where it came from or what it means or why we do it or what it connects to anything. I just need you to memorize it. That's like a recipe for you being like, I just could never remember that stuff. So Kayvon, will you ever have to do this? Like, will I ever grade you? Like, do you need to know how to do implicit differentiation? Yep. Do you need to know how to do the chain rule? Yep. Do you need to know the Pythagorean theorem? Yep. Would I ever have you just sit down and derive this for a quiz or test? Probably not. But every single element that you had to do here is mandatory, like it's expected. So, and the other side of the coin would be maybe you are a memorizer and you're like, you know what, frankly, I already have this thing memorized because I'm a very good memorizer. Good for you. But what if you have that one day where your mind just goes, and you're like, oh my gosh, I had this memorized yesterday and I totally know it. And you raise your hand, you're like, Mr. Anderson, what's the derivative for arcsine again? I'm like, I'm not going to tell you. And you're stuck. And I might even say, you could derive it. But if you never really bought into like where this comes from, maybe you can't, right? So that's my reason. It's just so you understand versus just my teacher told me a rule and sure enough it was in the textbook and I guess I'll do it because I have to. Versus like, oh, that makes sense. Things that make sense are actually sort of cool. Versus my teacher like opened my jaw and just like, slammed some stuff in my brain and whatever. So that's kind of the idea. Robbie, go ahead. It could. It absolutely could. So do you guys remember, this has been a while, so you might not remember this. Maybe you do. Maybe it was memorable enough. Do you guys remember the question from back in chapter 3? It would have been like October, and there was maybe November, and there was like a rocket taking off, and there was like a camera like trying to track with the rocket. Mm-hmm. We could have used, it would have been a whole lot easier to use like inverse tangent or inverse sine to answer that question. So yes, could easily be the answer to how do you figure out how fast an angle is rotating, for sure. Yeah, that's a very good point. Last thing I want to bring up before I set you guys off on your little journey with one of these is if you happen to look at your textbook, which I know some of you do, a lot of you don't, but if you do happen to look at your textbook and you looked at 5.6 and 5.7, you're going to see these presented slightly differently than the way that I do. I'm not wrong. They're not wrong. I like my way better because the main reason why we're doing what we're doing here is so that we can kind of do the stuff in 5.7. 5.7 is the kind of where we're headed. You need to know how to do this in order for that to make sense. And so I'm trying to make it more of a seamless transition between the two verses. Well, in 5.6 we looked at it this way. In 5.7 we're going to look at it this other way. I'd rather just kind of look at it all the same way. Again, they're not wrong. The book is fine. I'm not wrong either. I just like the smoothness of transition better. So I have a challenge for you, and I'm just looking around. Most of you have enough room. I clearly don't have enough room, so I'm going to do some erasing here. I would love for you guys to attempt to derive the derivative of arctangent of u over a. You've got the answer right in front of you, so you're going to know for sure whether you've got it or not. Can you get there? Try it. It's really similar to this one. It is quite similar. Details are different, but the idea is the same. Anyway, give it a shot. Here, so I was, if I'm going to be working with arctan, I'm going to write y equals arctangent of u over a. My next step would be there we go. Tangent of y is equal to u over a. Then I'd do d dx to both sides. That would give me secant squared of y times dy dx is equal to u prime over a. Therefore, dy dx is equal to u prime over a secant squared y. Good place to pause here because we've done a lot of good work if you got to this point, right? You got the dy dx in there and you got it isolated, but we need to deal with the secant squared of y. The way we deal with that, of course, is with a triangle. And we build our triangle based on this relationship between y, tangent, u, and a. So tangent of y is equal to opposite over adjacent, which would be u over a. Now, if we're going to be doing secant, we're going to need the hypotenuse, so you do the Pythagorean theorem real quick. A squared plus u squared square rooted. And then we finish it off by actually doing secant of y and squaring and all that good stuff. So we'd get dy dx equals, it'd be u prime over a times, so I don't know how you guys remember this, but I remember that secant is just the reciprocal of cosine, and cosine is adjacent over hypotenuse, so secant would be hypotenuse over adjacent, right? They're just reciprocals. So it'd be hypotenuse over adjacent, and let's not forget that we are supposed to be squaring the result, right? Because it's secant squared. All right, so this gives me u prime over a times a squared plus u squared, because the squared and the square root canceled, all over a squared. So there's a little more to this one, right? Because the a canceled out with one of the a's, and you still got to copy dot flop that a back up, right? So you end up finally with this going where it's supposed to go and be u prime a over, look at that, it's exactly what we were hoping to get. Anyways. Again, the goal here is simply understanding, and I guess the way I'd put it is if some pre-calc kid was looking over your shoulder while you did your homework and they're like, whoa, what are those A's and U's? What's that all about? And you're like, oh, that's the derivative of inverse sine. And then if their next question was, well, why? Well, like, where does that come from? If your answer was like, I don't know, the teacher just sort of wrote these on the board and I copied them down without thinking about it, that to me, that would be a really bad answer. A good answer would be like, oh, and like 2 minutes in, they're going to be like, okay, enough. I don't need to hear it. But at least you could explain it, right? You could say, here's where it came from, and it's cool because it makes sense, and all that good stuff. Anyway, so how you proceed with this is up to you. I would recommend that you do your homework and do it enough to the point where these naturally do become sort of memorized, but not because you just sat down and wrote and memorized them, just because you used them a lot, right? Anyway, so let's practice. Why don't you guys flip over? I think there's just 4 questions to practice here, just applying these things we've been developing. So ready, set, go. And I can help define the U and the A for you if you want, because that's really the thing. Like if you can, and by the way, it's arc sine and arc tangent are the ones that we're really going to focus on. We're not going to focus on arc cosine. So I wouldn't spend any more time than we already have on that one. So real quick, let's make sure that you all understand what the U and the A are. So for number 1 over there, what would you guys say the U would be? The U would be 2x. There are 2 different ways to think about this. If we thought about U being 2x, what would the A need to be? A would have to be 1. There's another way, so feel free to use that way if you want. Sam said, I think the U should be an x, and I'm okay with that. But if the U is x, the A would have to be what? 1/2. Operating on that right there, either way would actually work well. I'm going to go with this one simply because if I can avoid working with a fraction, I'm going to. There's just fewer things to keep track of. So that would work fine there. For number 2, real quick, what do you guys think the U is? 3x, and A is 5. Just A would just be 5. Remember, we set it up as U over A. And that's why, like when you said X was the U before, that's why we had to do the whole copy dot flop thing to make that work. Number 3, what do you think the A is? No, that's the U. The A would be 1. And then 4 is a little more clear. I'll let you guys kind of mess around with that. So let's take a few minutes. See if you guys can complete 1, 2, 3, 4. Please do check with a partner. See how you're all doing. Confirm your answers in a few minutes.
Square root of 1 minus 4x squared.
2 over the square root of 1 minus 4x squared is, I think, what she said. What do you guys think for number 1? Do you agree?
Yeah.
Hope you do. It's good. Real good. Nice job. Okay, number 2, maybe someone from over here, the left side of the room. Dax, Luke, Sam, Olivia.
I had 15 over 25.
Okay. Look at what Luke has up there. Do you guys have the same thing? I hope so.
If we didn't like simplify it down.
I don't think there's anything to be simplified. Or what do you mean? Like, did you have 5 squared plus?
Wait, I got 3 on the
Like,
top.
leave it as like 3 over.
Remember, the derivative of arctangent is u prime times a over a squared plus u squared. So the 15 is right.
No, but what if I simplified it down to like 3 over 5 plus 9 squared? Can I do that or no? Since no.
No. No. In order to cancel like that,
Have to be,
it has to cancel out of both terms in the denominator,
okay.
and it doesn't.
But if I was able to like factor it out and then.
Yeah, if something did factor out, of course you're welcome to do that. For sure. There's not a common 3. Yeah.
Saying 15.
I suppose you could factor a 3 out. It'd be 25 thirds. It could be done, but I'd just make it more of a mess.
Yeah.
All right. Anybody at this table have number 3? Derivative for number 3?
Yes.
You're all staring each other down. Anybody want to share?
So I got it.
Okay.
1/2 x to the negative 1/2 all over square root of 1 minus x.
You can always put the 2 on the
What do you guys think of that? So you agree with that? I do as well, but you could do a lot. Like you're suggesting, you could do a ton of stuff, right? So you could have x to the negative 1/2 over 2 root 1 minus x. But it's x to the negative 1/2. Why not move that one down too, right? So this could be 1 over 2 root x root 1 minus x. And then couldn't you multiply the 2 radicals together? I mean, you could end up with something that looks very different. So it could be that, if you wanted to. But I got to be honest with you and tell you, if it's a free response, I'm going with the purple box. Right? It's equivalent. It's great. It's correct. All that other stuff you'd only need to do if you had to match up a multiple choice answer. Okay. Any individual want to share what they got for number 4? Just anybody from the class? You guys? Oh, you did. I never asked you guys. I spaced out how many tables. You guys, tell me what you got for number 4. 7 over x squared plus 49. Did I write that down right? Okay. I thought it was u prime a. Why do you just have a up there? Hey, there you go. 7 times 1 is 7. Love it. Okay. It's great work. You guys have any questions? Okay. So then what I want to do is reverse course a little bit. We'll cover 5-7 on Tuesday. If you guys would, in your notes, let's go back just a little bit.
Yes.
Back past 5-6, back past 5-5. Remember this?
Yeah.
Long for your response we never touched.
She's back.
This is a pretty comical question. Once you get all the way done with it, comical in sort of a sad way. It's pollutant in some lake. Hey, guys. Whatever that is. Would you please do this? We don't have time to do all of this one today. Reason why I didn't do this one before is like these are all old applications, but those are going to be mostly the only applications moving forward, so we might as well keep practicing them. And so I'm thinking that right now we definitely have time for A and maybe B. So if you would, read this over. I'm going to just let you kind of read it yourself. And once you've had a chance to kind of read things over, attempt question A. This is a calculator active question, so you should be using that. Look at question A, maybe question B. and then we'll save C and D for maybe some other time when we got time to go back.
active, I'm guessing.
Definitely calculator active. If you are trying to figure out if the amount of pollutant is increasing or not, with P standing for the amount of pollutant, you've got to consider P prime, right? So here would be our thinking. If I could figure out P prime and I find out that P prime is negative, that means that P is decreasing. But if I find out that P prime is positive, that means P is increasing. So that's that old stuff from way back, chapter 3. So all I really need to do here is find P prime of 9. And of course, the good news is they gave me P prime, so all I have to really do is just plug it in. And it ended up being a positive number, is that right? Is it like 0.5? What? 504? Okay. So equals 0.504, which is positive. So we can say, therefore, the amount is increasing.
Well, I don't even think it's in there now.
That equals 9. Say again?
You have to put dates. Do you mark this off?
No, because I didn't say explain the meaning using correct units. I appreciate you trying to find it. Yeah. I fully admit it. Sometimes I forget to put things, but not in this case. It'll probably be the next one I'll mess up. But. I know for sure you're never going to miss that though, right, Jake?
No, I have.
No, I said moving forward, right? Because you're on it right now. You're like, I'm looking for that.
I'm going to put it on there every time now.
Okay.
Instead of spaces, he's going to put the units.
Well, don't make stuff up. Like, don't. Okay. I'm fine with that. I like it. All right. Do you guys have any questions on A? Listen, A has certainly the opportunity for you to fall into a trap of, it's a calculus class, therefore I better be finding a derivative of something or an integral of something. And the truth is on A, like I think I said this the other day, your skill level will actually be better shown by what you didn't do rather than what you did do. The fact that you didn't find a derivative or didn't find an antiderivative tells me that you know what P prime means. And you move forward. Anybody have any thoughts on B? Like, what'd you do with B? There you go. We're looking for a minimum, and so a critical point would be a candidate. So P prime of T equals 0 makes a lot of sense. Did you solve it? Did anybody do what Julia did and solve?
Yeah, 5.49.
Okay, so, and it was just the single critical point? 5.493? Okay.
3-1. If you want to go forward.
Sure, why not? Okay, so then what's cool about this for B is that's the only critical number in town, right? And so then even when you think about the endpoints, if you think about your graph, like from the far left to the far right, that's the only critical point. So to the left of the critical point, what's the value of P prime? Is it positive or negative?
Negative.
And then to the right, I'm assuming P prime becomes positive. So you could say something like P prime is negative on the interval 0 to 5.4931, and P prime is positive on the interval 5.4931 to infinity, I suppose, right? Therefore, P is minimized when T equals that 5.4931. That make sense?
Or you could use math 9, right?
Math 9. Where would you use math 9? Oh, we're not there yet. That's actually going to be for C.
Oh, whoops.
I suppose you could, but you'd have a really have a hard time with your right endpoint.
Mm-hmm. True.
So you'd have to kind of come back to this way of thinking. You'd have to say, well, there really isn't a right endpoint because how long could time go on for? We don't really know. There's not really a definitive end to this. But yeah, moving on to C, math 9 will be a thing. But we'll talk about that later. We'll find out whenever we finish this. We'll find out whether that lake really is safe for you to be swimming in, and if the investigator is really serving the public well. Perhaps not.